the integral from 0 to infinity. And what that means is the integral is bound from the point 0 to an infinite point. And our function is going to be e to the negative x squared cosine of 5x. And it's all with respect to x. So if you know anything about calculus, you can stop the video now and try to solve that integral using the standard techniques and the fundamental theorems of calculus, maybe u substitution or integration by parts using u and v substitution. What you'll find is that it's nearly impossible to do that with integration by parts or u substitution or any standard fundamental technique that you would use for this problem would be almost useless, unfortunately. This is where the blending of worlds comes in. We're going to use a technique known as the Feynman technique. Surely it's been called many other names, and it surely wasn't originally noticed by Feynman, though he's who it's famous for in the modern time. So a little backstory. Richard Feynman's a famous physicist from the mid-century, 20th century, and he revolutionized how the subjects in physics themselves were taught. One of the infamous things about physics is that it has a super complex nature to it. And it's even myself, when somebody asks what am I studying in school and I say physics, they get the whoa kind of look on their face. It's not really that physics is this overly complex area. It's just a strange subject, and it's so small in people that actually study it that it's got this strange nature to it, that it's this far off entity that only the few can accept and actually understand. That's not the case at all. And Richard Feynman showed that through how he taught. He put together a series of books known as the Feynman Lectures on Physics and several other books such as QED or 6 Easy Pieces or something like that. But all of his books are extremely easy to understand and easy to read for any level of reader, essentially. And that's what he really wanted to do. He widened the basic pool of people that you could pull from to actually be able to study physics, because it dropped the complexity. So he noticed a technique that you could use with difficult integration. It's been known as the Feynman technique. It's also been called differentiating under the integral sign, which I'll show you what that means shortly. But it's going to allow us to solve this ugly integral. So first and foremost, let's generalize this integral, because what we have is the integral of 0 to infinity of e to the negative x squared multiplied by the cosine function of 5x with respect to x. Let's generalize this. So let's call it some function of alpha. So a function of alpha, and it's still bound from 0 to infinity with our exponential multiplied by cosine of alpha x. And the function's still with respect to x. I wanted to denote the alpha in a different color. So alpha is just a parameter here. We can tell it to be anything we want to now. It could be our 5 like it is in the original problem. It could be a 0. It could be a 10. It could be a 4.79138 times 10 to the 12th if you want it to be that. Alpha could be anything now. What this is going to allow us to do is fiddle around with and manipulate the problem algebraically to see if we can solve it. So what we're going to do, this allows us to work with it as an algebraic expression. And now we're going to derive both sides, essentially. So if I take the derivative of both sides, which I could do algebraically, because as long as I keep the same operators on both sides of the equation, it's still equal. So we're going to take the derivative of both sides here, derivative with respect to x. Where is my black marker? Derivative on this side. Derivative with respect to x of this integral bound from infinity, e to the negative x squared, cosine of alpha x, all with respect to x. Where's our red marker so we can put in the alphas? Alright, so now let's go ahead and do this differentiation. If we derive the right side or the left side of the problem, we can switch it to Newtonian notation to get rid of the Leibniz notation. Just basically we're dropping the d's, the x's, and the alpha. So this is going to be f prime of alpha. But we can drop the alpha. Sorry about that. So this is f prime. On the right side, we're going to bring the derivative inside of the integrand. And what that means, this is the Feynman technique. So this is what's called differentiating under the integrand. And what happens there is the derivative changes from a full derivative to a partial derivative, still with respect to x. Now the only difference in between a full and partial derivative is a partial derivative treats all other values other than the variable as a constant. So it's going to treat this alpha essentially as a constant and all these other values as a constant. So we can take the derivative on the inside now, this partial derivative. This is going to tell us the integral 0 to infinity. So when we take this partial derivative, and we're still with respect to x here on the inside, we end up with the x that we're looking for to actually make this problem solvable. We get negative x e to the negative x squared sine of alpha x. We want to keep base, we want to make our alpha red. Sine of alpha x. And it's still with respect to x. This is great, because now if you look at this, this is something that we can work with algebraically. We can work with integration by parts now. So let's get a little space, go on the right side. If you don't remember your fundamental calculus classes, Calc 1 and 2, integration by parts, essentially you've got the integral of v du is going to be equal to u times v minus the integral of, oh, I'm writing this wrong, aren't I? I am. Huh? See, this is why it's good to have your notes. So, let's try this again. Integration by parts. Integration by parts is when you have a standard integral of u dv. It's going to be equal to u times v minus an integral of v du. So this is a type of substitution just like u substitution. Essentially what we're looking for now are portions of the equation that we can actually work with. So we take a look at it here and let's do some substitutions. So we know we're going to be integrating the dv side essentially to get v. And we know we're going to be differentiating u to get du. So we're looking for a u and we're looking for a dv to start. So we look here, basically we're looking to see which one of these functions is easier to differentiate and which one of these functions is easier to integrate. In finding, you'll see that, well, sine of alpha x, that's easily differentiable. So sine of alpha x, when we differentiate that to du, what do we get there? We get cosine from the sine and alpha x. Chain rule activates and gives us alpha up front since it's still with respect to x. We're still working in x. Then on the right side, dv, we get what's left over. The negative x e negative x squared dx. Excuse me. So when we integrate this, we basically integrate both sides. We get v, as the integral of dv is v. So the integral of this on the right side, just basically just working in our head, we'll end up with 1/2 e to the negative x squared. So we take these values and we plug them into our integration by parts. So we get the u times v. So what is that? U is going to be sine of alpha x. Oh, we're not keeping base, are we? We got to get our red for our alpha. Sine of alpha x. U times v. V was 1/2 e to the negative x squared minus integral of v du. And the integral is still bound from 0 to infinity, and this is part of our answer, so it's also bound from 0 to infinity. And v is 1/2 e to the negative x squared, and du was alpha cosine alpha x. So alpha cosine alpha x, still with respect to x. Alright, so now we can do a little manipulation here and just simplification to make everything a little bit more nice. So we have sine of alpha x over 2, we can bring the e, since it's got a negative down, e to the x squared. And of course this is still bound from 0 to infinity. And minus, we can pull the alpha over 2 out. So we pull the alpha over 2 out, since it's just a constant, still 0 to infinity of e to the negative x squared cosine of alpha x dx. Oh, and this is great. Check it out. So you should recognize this, because this is our original f of alpha. So this portion here is our f of alpha. That's great. So here we actually have the function. This tells us that the integration by parts is actually working, because now we're going to be able to do some algebraic manipulations, and even further, we can solve this portion on the left. And if we solve this portion on the left, let's just take it down over here for a minute. So we'll evaluate it at the bounds. We have sine of alpha x, and we're multiplying an infinity here for the top bound, so this is just going to be sine of infinity divided by 2e to the infinity squared, so infinity again, and this is going to be minus sine of, well, 0 times anything is 0, so sine of 0 divided by 2e to the 0, and e to the 0 is 1, so it's just divided by 2. Well, that's going to equal, what, 0 minus 0, which equals 0. So that's beautiful. So a little further, well, then we've got 0 minus alpha over 2 integral 0 to infinity e to the negative x squared cosine alpha x dx, which is our original function. And if we recall, this entire equation is equal to our f prime. So this is f prime of alpha. All right, this is great. So let's just rework it and throw in a few different names for things. So we have f prime, we're going to drop the alpha, equals, well, we can drop the zeros. This is negative alpha over 2, and this was f, so that's just f. Well, if you know or don't know, this is actually a first order separable differential equation. And it's great that it's separable, because that means we can solve it. Differential equations are just a specialized type of equation that deal with a higher order than the original function itself within the equation as well. So we're looking at parameters that are differentiating from one another, and they move around based off of a certain value. So let's bring back the Leibniz notation. So we're going to have df d alpha is equal to negative alpha over 2f. All right, so let's move things around. Then we have 1 over f df is equal to negative alpha over 2 d alpha. And we can solve this. So integrating both sides, we get the integral on the left side is just going to be the natural log, absolute value of the function. And the integral on the right side is, what do we have here? So negative alpha squared over 4. And it's not a bound integral, so we have to add in our constant of integration plus c. Alright, well, let's get the function by itself, and how we get rid of a natural log is we can raise it all to an exponential, and keeping algebraically basis, raise both sides to the exponential. So this will give us f. Well, if you raise all of this to the exponential, you can rework it. We're going to get a secondary constant here because of the absolute value. So this will be c2 and e to the negative alpha squared over 4. And this is our f of alpha. Well, how does that help us? We have another constant in here now, and we still had a constant in the original equation, and we're not sure what's going on now. Well, this helps us greatly, actually, because we can take a look at this, and it's f of alpha. This is also f of alpha, so we can basically equate these values and see if there's anything the original will tell us about this. So e to the negative x squared cosine of alpha x, still dx. Well, we never liked this cosine in here. This cosine was the thing that was bothering us the whole time. So let's just let alpha be 0. Because if alpha is 0, this is cosine of 0, and cosine of 0 is 1. Well, then this will go to, adding in here, we get c2 e to the 0 over 4. Well, e to the 0 is just 1. And this will equal, well, cosine of a 0, of course, is 1. So we have 0 to infinity of e to the negative x squared dx. And look at this. This is actually a famous integral. This is the Gaussian integral. And the Gaussian integral has a very specific value. So this tells us that c2 is equal to square root of pi over 2. So that means that our function, remember our function c2, we just add in this value, is the square root of pi over 2 e to the negative alpha squared over 4. Beautiful. So we take it back to our original problem, the integral where alpha was 5. So alpha equals 5. Then the integral 0 to infinity e to the negative x squared cosine alpha x dx equals root pi over 2 e to the negative 5 squared, or 25, over 4. And there's our answer. Using the Feynman technique, we were able to solve this integral. It was a seemingly long problem, but really that's not the case in calculus. It would have been a much, much more complex problem if you would have started with integration by parts, because you would have just kept going and going. You notice within the problem itself, we still use the IVP technique. We still used a type of substitution. So even when we used Feynman's technique, we still went back to our basis and worked on a fundamental section of calculus. I hope you enjoyed this follow through with this problem, and look forward for more videos in calculus, and I'm glad you joined me. Thank you.